For this one, we're going to sketch the graph of x squared e to the x. Same steps. We'll start off with domain. All reals. Nothing to worry about here. No fractions, no radicals, no logarithms. Bye. Symmetry. We're not going to have any. Because if we put in negative x in for x, we do not get back what we start with. We don't get the negative of what we start with. So no no y-axis or no origin symmetry. What are you going to do? Intercept. X-intercept is 0 equals x squared e to the x. That means either x squared equals 0 or e to the x equals 0. Well, e to the x never equals 0. So this guy tells you that x equals 0. But if you have an x-intercept to be 0 and you have a function, that means your y-intercept must also be 0. So we only get 1 point here for this step, 0, 0. Vertical asymptotes holes? None. When your domain is all reals, there's nothing to worry about here. It's numbers that aren't in a domain you have to worry about. E. What do we got? Horizontal asymptotes, oblique asymptotes. I really should have called this end behavior in the previous example, but it was okay because that one was a rational function. So if we consider the limit as x gets really big, well, x squared gets really big, e to the x gets really big, so their product gets really, really big. This guy goes off to infinity, but limit as x goes to negative infinity of x squared e to the x. Uh-oh. This guy goes towards infinity. This guy goes to 0. Does that look like anything? Of course it does. It looks like an indeterminate form. So we have to rewrite it so that it's ready for L'Hopital's. Here we go. Do the limit as x approaches negative infinity. Let's keep x squared upstairs. So now as we approach infinity, we get infinity over infinity. So we're all set up for L'Hopital. So applying L'Hopital, we get 2x over negative e to the negative x, which again is another infinity over infinity. So we have to do L'Hopital's again. We get 2 over e to the negative x. But now as we go towards negative infinity, forgot my little negative sign there, we get 0, which means you have a horizontal asymptote at y equals 0. Who thought that L'Hopital's is not coming back? I bet you did. Yes, I know what you're thinking. Okay. Next up, we have increasing, decreasing, relative extrema. We have to find the first derivative. Don't forget your product rule. The first derivative will always exist, which is nice, so we really only have to consider where it equals 0. They both have a factor of x, e to the x, so we can pull that out. Doing so, we're left with x plus 2. Setting each factor to 0, we get x to be 0 and x to be negative 2, because again, e to the x is never 0. So, making a little number line, we get plus, minus, plus. So we are increasing from negative infinity to negative 2, and then 0 to infinity. We are decreasing everywhere else. Since -2 and 0 are in the domain, they cause sign changes and they make the first derivative equal to 0. We have relative extrema there, namely at -2, since it goes from increase to decrease, that's a relative max. And that'll be at -2, 4, e is a -2. And relative min at 0, 0. How nice. So sorry that it keeps bouncing like that. So our x and y intercept happens to also be a relative minimum. And then g. I'm going to put g up here. Look at all this space. We'll do concavity and inflection point, which requires the second derivative. All right, second derivative. That's pretty ugly. Well, notice we get x squared e to the x. That was our original problem, so that means we're going to get all this right back again. So that's the derivative of the first term. The second term will be the exact same thing. I lied. It won't be the same thing. So first times derivative of the second plus second times derivative of the first. All right. I think we have some like terms here. We do. That makes 4x. And they all have an e to the x. That's a 4 there. Ha! That's unfortunate, because that does not factor nicely. Oh well. So this always exists, which is nice, so we don't have to worry about the second case, but we do have to worry about where the second derivative does not equal 0. E to the x is never 0, so we're really just looking at this quadratic here. I'm going to leave it to you to find out that x is -2 plus or minus the square root of 2. You probably need your quadratic formula there. Drawing the number line, picking some test points, you should get plus minus plus. Since both of these numbers are in the domain, they cause the second derivative to be 0. And as a sign change, we do have inflection points. But first things first, we are concave up to the negative, to the left of -2 minus radical 2. And then again to the right of 2, sorry about that, plus -2 plus radical 2. I did it again. No one has to know. We are concave down between those two values. I really want to draw a comma. Okay. And we have an inflection point in -2 minus radical 2. And a -2 plus radical 2. We would get those y values by putting them back into the original function. So the exact value, as you might guess, would be the x-coordinate squared and then the e raised to the next x-coordinate. Now when you have a problem like this and you have to graph it, decimals are fine to get an idea of where the point should be. But if I ask for exact values, I will want to look for that glory. All right. Draw a number line. Actually, I'm going to do this on the next page. Draw a number line. We're going to put in all of our critical numbers. They are -2 and 0. And then we had -2 plus radical 2 and negative 2 minus radical 2. Well, negative 2 minus radical 2 should be here. And radical 2 is about 1.4, which does not make it big enough to surpass 0 when we add it to negative 2. Okay, so from our first number line right here, we know we're increasing to the left of negative 2 and to the right of 0. So this is increase, increase, and increase here. And we're decreasing everywhere else. And then we have concave up to the left of negative 2 minus radical 2 and to the right of negative 2 plus radical 2. So this is concave up. And these are concave up. And these guys were concave down. We have 5 shapes. So increasing concave up, increasing concave down, decreasing concave down, decreasing concave up, increasing concave up. All right, let's draw a graph. X-intercept 0, 0, same with the y-intercept. I don't know why it does that. I think it hates me. There we go. Horizontal asymptote at y equals 0. I'll draw that in red. Now your graph is in 3D. You're welcome. No vertical asymptotes. We have a relative max at negative 2, comma 4, e to the negative 2. Negative 2, 4 e to the negative 2. I'm way too lazy to go look that up. I'm going to just say it's right there. I know it's positive. And then let's see, that's a relative max. We have a relative min at 0, 0, check. We have an inflection point at negative 2, negative minus radical 2, comma whatever that number is. Ew. Okay, so it looks like the one is at 0.38 and the other one is 0.19. All right. I can do it. 0.38. Oh, change color. 0.38. That looks good. And then 0.19. That looks good too. All right. And okay. And we know we have to follow along this horizontal asymptote. So this piece here goes to the left of this point. Go along your asymptotes. This piece here connects this point to this point. This piece here connects these 2 points. This piece here connects the next 2 points, but it has to go through your relative min, x-intercept, and this point here goes for everything else. Hooray! That's, why did it erase it again? I wanted to draw a smiley face. You know what, I'll just draw it up here. Take that, graph.